For decades, there's been this one huge challenge, right? How do we build an engine that's got all the power we need, but doesn't wreck the planet in the process? Well, today, we're going deep on one of the most exciting ideas out there, a way to use hydrogen to make the good old internal combustion engine radically cleaner.
All right, so here's our game plan. First, we're going to break down the basic problem every engine designer is up against. Then, we'll ask the big question, is hydrogen the magic bullet we've been hoping for? After that, we'll explore a really clever engineering trick to make it work, check out its performance report card, and finally, we'll look at what the future might hold for the hydrogen engine.
Before we can even talk about the future, we have to get a handle on the present. And right now, the undisputed king, the workhorse of pretty much all global industry, is the diesel engine. But the very thing that makes it so amazing, that intense, high heat, high power combustion, is also its biggest downfall.
And here's the deal with diesel, laid out plain and simple. It's a trade-off. On one hand, you get incredible power and efficiency. It just works. But on the other hand, to get that power, you need super high temperatures. And that heat cooks up a nasty cocktail of pollutants, especially nitrogen oxides, or NOx, and that black sooty smoke. This is the fundamental conflict engineers have been wrestling with forever.
Okay, so if the fuel is the problem, why not just use a cleaner one?
And that brings us to hydrogen. I mean, on paper, it looks like the perfect, ultimate solution to the whole diesel mess. But, as you might have guessed, there's a big catch. I mean, just look at these stats. Hydrogen seems almost purpose-built for a clean engine. It has way more energy packed into it than diesel does, it burns super fast, super stable, but the real magic, the absolute game changer, is what it doesn't have. It has no carbon. And if there's no carbon going in, there's no CO2 coming out. The only thing you get is water. It's basically the dream fuel, in theory.
And here it is. Here's the catch. A diesel engine works by just squeezing the fuel and air mixture so hard that it gets hot enough to spontaneously combust. No spark plugs needed. But hydrogen, well, it's a bit stubborn. It needs to get way, way hotter than diesel to ignite on its own. So you can't just swap it in. The engine physically can't squeeze it hard enough to set it off. The physics just don't work.
So what do? Well, this is where the engineers got really clever. They realized instead of trying to force hydrogen to act like diesel, why not just change the rules of the game entirely? And that led them to this concept called low temperature combustion.
The basic idea behind LTC is actually pretty brilliant. Remember how we said the high heat of diesel combustion is what creates all the bad stuff like NOx and soot? Well, LTC sidesteps that problem completely by making a very thin or lean and perfectly mixed blend of fuel and air. This mixture burns much, much cooler, which means those pollutants never even have a chance to form. You're not cleaning up the exhaust pipe, you're just not making the mess in the first place.
Now, the first flavor of this is something called HCCI. The goal here is to make a totally uniform or homogeneous mix of fuel and air. And as the piston moves up, the pressure builds and then, bam! The entire mixture ignites all at once, like the whole room just flashing into flames simultaneously. It's incredibly efficient, but, as you can probably imagine, it is spectacularly difficult to control. It's a bit of a wild horse.
And that brings us to the next evolution, which is way more sophisticated, RCCI. This is where it gets really cool, because it uses two different fuels. So first, you fill the cylinder up with air and your low reactivity fuel. That's our stubborn hydrogen. Then, right when you need it, you inject a tiny little squirt of a high reactivity fuel, like diesel. That little bit of diesel acts like a whole bunch of tiny spark plugs, creating hot spots that trigger the main hydrogen burn in a much more controlled way.
And this just lays it all out, doesn't it? HCCI is simple on paper. One fuel, mix it all up. But it's a nightmare to control in the real world. RCCI, though, by using two fuels, gives engineers a bunch of knobs to turn. They can change the timing of that little diesel injection to perfectly manage the combustion. It's more complex, for sure, but that complexity is what gives you control and a much bigger, more stable operating range.
Okay, so let's walk through this, step by step. What's actually happening in that cylinder? First, the hydrogen gets mixed into the air as it's being sucked into the cylinder. Then, pretty early on, you get that small shot of diesel. And finally, as the piston comes up and everything gets squeezed, the pressure and heat ignite those little diesel pockets, and that ignition is what sets off the main hydrogen-air mixture in a nice, clean, controlled burn.
So that's the beautiful theory. But does this hydrogen diesel combo engine actually deliver the goods? Let's take a look at the performance report card, and you'll see there are some incredible wins and some brand new challenges.
First, let's just get to the headline. This is huge. At lower engine loads, which is, where most of our driving and operating actually happens, this tech can cut CO2 emissions by a mind-blowing 97% compared to a regular diesel engine. That's practically zero. It's an absolutely game-changing number.
And it's not just the CO2. Take a look at the soot. You can see it right here. Because we're doing that pre-mixed, cooler burn, the conditions that make all that black soot in a normal diesel engine, they just don't exist. The exhaust comes out dramatically cleaner. It's a night and day difference.
But it's not all good news. With all this fast, powerful combustion, you can run into a new problem. It can get too violent. It creates this condition called knock, or ringing, which is bad news for the engine. And engineers have actually put a hard number on it, a safety limit of 5 megawatts per square meter of ringing intensity. If you go past that, you're literally in danger of damaging the engine. So you're always walking this very fine line.
So here it is, the final scorecard, the pros and the cons. And you can see the pros are massive, way lower NOx and soot. But the cons are real too. That cooler burn that's so good at cutting NOx can sometimes be a little too cool, so you get incomplete combustion. That means more unburned fuel, or hydrocarbons, and carbon monoxide coming out the other end. Plus, you're always fighting to stay in that narrow operating window to avoid that dangerous knocking. It's a huge leap forward, for sure, but it's not quite the perfect silver bullet yet.
And all of this brings us to the really big, really important question. Given all these trade-offs, where does this technology actually fit in? Is it the ultimate destination for clean power, or is it maybe just a bridge to get us somewhere else?
The road ahead still has some pretty big bumps. Researchers have a to-do list. They've got to figure out how to control that knocking when the engine is working really hard, find the absolute safest amount of hydrogen you can use, develop special hardware like flame arresters for safety, and of course, solve that nagging issue with the unburned hydrocarbon emissions.
But this leads to a really elegant potential solution. If this hydrogen engine has this narrow, sweet spot where it's super clean and efficient, well, why not build a system that just lets it live there 24/7? Imagine pairing it with an electric motor in a hybrid vehicle. The hydrogen engine could just run at its one perfect speed, acting like an ultra-clean generator for the batteries, and the electric motor would handle all the starting, stopping, and changing speeds of driving. You literally get the best of both worlds.
And so that's what we're left with, this big, provocative question. Is this kind of super clean hybrid engine the final answer? Is it the destination? Or is it a brilliant, crucial, but temporary bridge technology, something that helps us get off fossil fuels while we build out the massive infrastructure needed for an all-electric or maybe a hydrogen fuel cell future? The jury is still out, and the debate is very much alive.